and he will speak on Pontryagin duality to finite groups. I've been asked to say a few words about the speaker and or the subject, but Partho told me not to say anything about him, so I will speak only about the subject. He works in the area called non-commutative geometry. Now, of course, there are undergraduate students in the audience, so let me say a little bit about what this is. Algebra, of course, we can imagine what non-commutative algebra is. We have non-abelian groups or matrices, rings of matrices. These are non-commutative objects. But what does it mean for geometry to be non-commutative? So the origin for this lies in the connection between algebra and geometry. If you take a topological space, and if you think of that as studying geometry, then the rings of functions on this space, they form a commutative ring. And a theorem assures that studying this ring is the same as studying the space. So in some sense, geometry gets converted to algebra by studying functions on spaces, on topological spaces. And now we can naively say, well, if studying commutative rings is the same as studying topological spaces, we just relax the assumption of commutativity and study non-commutative rings. Of course, we'll have to study only certain kinds of non-commutative rings in order for things to be interesting. And what kinds of rings we study and what kind of objects form replacements for classical geometric objects such as manifolds, this forms the subject of non-commutative geometry. And this is Partho's area. So without much further ado, I request.
So firstly, I would like to thank the organizers for this opportunity. And then Raghavan said that I should talk about aspects, it is called history aspects and prospects of mathematics by aspects in India, so that in India part was there. So I thought I should talk about something about which there are a couple of people in India work and so on. And just now I was pointed that in this title I should have put these two words. So Pontryagin duality is a statement about abelian groups. But I want to talk about Pontryagin duality for finite groups. So it is not exactly Pontryagin duality, but an extension of that. So it should have come within quotes. And then we want to extend the concept of finite groups also. So that also should have come within quotes. So there are lots of quotes which I have omitted. So it is Pontryagin duality for finite groups. And I see some of you are taking notes. You need not take any notes because I will keep this thing in my web page. So you can listen to it and later on download and go through the material. You can concentrate on this, whatever I am doing now. So we first want to motivate this thing that classical formulation of Pontryagin duality, it is a statement about finite abelian groups. So you restrict on finite abelian groups. So let us first focus on linear algebra. We have a finite dimensional vector space over complex numbers. So throughout I may drop these complex numbers, but all the vector spaces are over complex numbers. So if we have this, then there is another standard. So and we have a basis E1, E2, En. Given this, we can form another vector space, namely dual of V. So we have a standard space complex here. So we consider all possible linear maps from V to C, and it is called dual of V. Now this space is also n-dimensional, and the basis of this is given as follows. So you consider linear functionals phi. So phi I of Ej is like delta Ij. So it is 1 if j equal to 1, otherwise it is 0. And of course, these functionals phi 1, phi 2, phi n, they form a basis for V star called dual basis. And as we have this concept of dual of a vector space, we have this concept of dual of a linear map. So we have a linear map T. Then its dual is a map from W star to V star, which is defined as follows. So T star of phi acting on V is phi of TV. And then this dualization follows this property that if we have two maps, then S, so T from V to W and S from W to U, then S composed T star is T star composed with S star. So remember this identity. This order of these operators are interchanged. So S composed T star is T star composed with S star. So remember this. Now the proposition is the following, which we have seen, that if we have a finite dimensional vector space V, and then we have this natural map phi V from V to V star star. So given by phi V of, V acting on a functional. So, elements of V star. So, phi V of V is an element here, that means these are functionals on V star. So, I take a functional from V star which is phi. So, phi V of V acting on phi is phi V. So, the proposition says that this gives a natural isomorphism between V and V star star. So, the word natural isomorphism is kind of course, it is natural, but there is a precise sense to it. And so, how does one prove it? So, you take phi j of phi V E I. So, this is a functional on V star, and if you compute this object, then you see that this is same as phi j of E I. So, these quantities phi V E I, they form the dual basis of this one. So, that proves that these quantities is the dual basis. So, we have a map phi V which takes a basis and maps it to a basis. So, phi V must be an isomorphism. And the meaning of naturality is the following, that so if we have vector spaces V and W and a map T, then of course we can talk of this map T star star, and it means that if you consider this composition, namely you first apply phi V, then T star star, that is same as you first apply T and then phi W. And this way of saying kind of equality of two operators is very useful, and we will use it throughout. Now, we can move to Pontryagin duality. So, suppose we are given a finite abelian group G. It is just like this case where you have a finite dimensional vector space V, and now in that case we had a standard vector space, namely C. See, we have V, we have a standard vector space C, we consider all possible linear maps. So, same thing here, we have a abelian group, we fix another standard abelian group, namely group of complex numbers with modulus 1. And then we consider this set, namely group homomorphism. So, from G to S1. So, that means phi of identity is 1 and phi of G1, G2 is phi G1, phi G2 maps of satisfying these conditions. Now, this set G hat, this is a group called Pontryagin dual of G. And what is the product rule? Product rule is the following. So, I take two functions phi 1 and phi 2, their product at G is phi 1 G, phi 2 G. And what is the inverse? Phi inverse of G is phi G inverse. Identity is the constant function 1. So, you can verify that this is a group. And then of course, to get some feeling about this group, let us see how does it look like in some concrete cases. So, suppose G is a cyclic group of order n. So, G is 0, 1 up to n minus 1 with addition modulo n. Then suppose we have a homomorphism from G to S1. That means that phi assigns values to these things which take value in S1. So, phi of 1 is a number, and of course, if I add 1 n times in this group, I should get identity. That means that z power n is equal to 1. So, there is a correspondence, namely if I map this group element phi from G hat to phi of 1, then this map is a bijective correspondence, and phi 1 takes value in this set. So, set of nth roots of unity, and as this is a bijective correspondence and it preserves the group law, this shows that this set G hat. So, G hat is the collection of all these such homomorphisms phi, and phi's are specified by specifying phi 1. So, G hat is isomorphic with this group, and note that this is also a cyclic group of order n. So, there are two things to note. Firstly, if you are given an arbitrary element L in this group, then there exists a element in the dual such that phi of L is not equal to 1. So, you can take more precisely phi of 1 to be this quantity, then phi of L will be e to the power 2 pi I L over n. So, that is not equal to 1. And secondly, G is isomorphic with G hat. That is not the point. Point is that they have same cardinality. In the vector space case, while we are arguing, we argued that this map phi, capital phi v, that map is natural, and so it maps one basis to another basis. So there is a kind of counting argument. So here also the counterpart of that counting thing is that G is isomorphic with G hat. But this isomorphism, so one should be careful about this isomorphism is not natural, meaning I can take a generator of this group. There could be many generators, and then I can map it to any generator of this group. So this isomorphism is not natural, even though they are isomorphic, but they are not naturally isomorphic, but they have same cardinality. So of course, once you have understood this concept of dual for cyclic groups, we should look at direct sums. So suppose I have a group G, which is a direct sum of G1 and G2. Then suppose I have a function phi from G to S1, then I can restrict phi to these components, and that gives me elements phi j in G j hat. So an element in G hat determines a pair of element phi j. In the other direction, suppose I am given a pair of elements phi j here, then I can define an element phi in G hat as follows. So elements of these are pairs G1 comma G2. So if I define phi of G1 G2 is phi 1 G1 phi 2 G2, then this phi will be an element of G hat. So there is a bijective correspondence, and this correspondence also kind of respects the group structure. So phi going to phi 1 comma phi 2 gives an isomorphism between G hat and G1 hat cross G2 hat. Similarly, instead of a direct sum, if I had taken a product of two groups, of course two abelian groups, now everything is abelian, then we have this isomorphism that G hat is isomorphic with G1 hat direct sum G2 hat. Again note that cardinality of G is same as cardinality of G1 into G2, that is same as these and same as G hat. So these cardinalities match. So here is this theorem, which is kind of analogous to this statement. V is isomorphic with V star star. So G is naturally isomorphic with G hat hat, and the map is very similar to that one. So you define a map phi G from G to G hat hat. So phi G of G, this is an element in G hat, this is an element in G hat. That means it is a homomorphism from G hat to S1. So phi is an element in G hat. So it acts on phi and should give a complex number of modulus 1, that is phi of G. So now we want to prove that this assertion that G is isomorphic with G hat hat if G is cyclic. So phi G is 1 to 1. So suppose phi G of G on phi is 1 for all phi in G hat. Okay. So what does it mean? That means that, okay, so why is it so? Suppose phi G of phi equal to 1 for all phi. Now let us ask this question, that is it possible that this element of G hat, no, this is an element in G hat hat. So say so this says phi G equal to 1 for all phi in G hat. So let us ask this question, can it happen that G is not equal to identity? And let us go back to this one. If we have something L in G, L is not equal to 0, that means L is not the identity in G, then there is always a phi such that phi of L is not equal to 1. So that implies that if phi of G equal to 1 for all phi, then G must be identity. So this shows that phi G is 1 to 1, and of course we have this thing that they are same in numbers. So I have a 1 to 1 homomorphism from G to G hat hat, therefore it must be isomorphism because they have same cardinality. So let us ask this question again, that whether this assertion holds for a direct sum. So suppose I have a direct sum G equal to G1 direct sum G2, where these maps are isomorphisms. then we have this chain. So, G hat hat is like, so G hat is G1 hat cross G2 hat whole hat. Now, this is same as G1 hat hat direct sum G2 hat hat. I just stated these things in the last slide, and that is same as G1 direct sum G2 equal to G. So, we have isomorphism in if G is cyclic, then we have this isomorphism. If G is direct sum of cyclic groups, then also we have an isomorphism. And since an arbitrary cyclic group, arbitrary abelian group is finite abelian group is direct sum of cyclic groups, this assertion holds. Now, only thing is that we should point out what does one mean by saying something is naturally isomorphic. Again, as in the vector space case, so we can define dual of a homomorphism. We define dual subgroups. I can define dual of a homomorphism, namely, I have same prescription. F hat of phi on G is phi of f of G. And then naturality means if I have a homomorphism F, then this diagram commutes. That means if I apply this followed by this is same as phi h composed with F. So, this is the meaning of Pontryagin duality that says that G and G hat hat are naturally isomorphic. And then of course, we want to ask that so far it was only for abelian groups. What happens if we drop the abelian condition? And first thing is that this thing G hat, this set could be trivial, meaning it could be a trivial group. So, if G is simple, that means, and if G is simple and not abelian, then there cannot be any non-trivial homomorphism into complex numbers. So, G hat is the trivial group. Another difficulty, G, this is always abelian. Therefore, if G is not abelian, one should not hope to have something like this, because G is non-abelian, this is always abelian. So, these two cannot be isomorphic. So, the point is that if we want to extend this concept beyond abelian groups, then we must reinterpret the concept of groups, and that is basically the point. And of course, here as I am presenting, it looks like that as if to prove this theorem, or just meaning just for fun one is extending this theorem, but it is not like that. So, in reality it happens like this, that kind of man interacts with nature, and then of course in nature things are happening, we are observing things, and then we conceptualize. As we conceptualize, that is the point of transition into mathematics. We conceptualize our surroundings, and then of course as we probe our surroundings in a better way, our vision or understanding of nature of all our surroundings improves. In that sense, as we probe the concept of space around us, some finer details emerge, and it looks like that the concept of space need to be reorganized. And as that concept is extended, as Vijay mentioned, by making things non-commutative, these spaces has got more symmetries. And to understand those symmetries, actually one extends this and then realizes that this transition from our ordinary understanding of spaces to non-commutative spaces, or understanding of the symmetries of spaces to the symmetries of these non-commutative spaces, all these transitions are parallel, and these transitions could be understood in an algebraic sense by making things non-commutative. So, here is one instance of that. Here we are emphasizing the mathematical part, namely that this extension allows you to interpret things known for abelian groups beyond that, but there is a need for doing this, which is even other outside mathematics also, for understanding nature and so on. Of course, I do not know about that part very well. I understand only the mathematical part, but anyway, there are need for doing this. So, there is a genuine need for extending these concepts, and for doing that extension, we need some more algebra. So, this is a crucial concept, and let us spend some time on that. So, we have vector spaces U, V, W. Suppose we have vector spaces over complex numbers, and then we have studied linear maps, but there could be maps which are not linear, but which are nice in some sense. So, these are called bilinear, or in general multilinear maps. So, they are defined as follows. Suppose T is a map from U cross V to W. I say T is bilinear if T satisfies this condition, namely T of A U1 plus B U2. Say A, B are complex numbers, U1, U2 are elements from this vector space, comma V is A times T U1, comma V plus B T U2, comma V, and also Same thing in the other variable, such maps are called bilinear maps. And here is an example. You consider this map T. So, MNC is the algebra of matrices, and y and matrices are complex numbers. So, you take two of those, and T is given by A comma B going to the product A dot B, and you see that this map T satisfies these conditions. Namely, A1 plus A2 dot B is A1B plus A2B, or A times B1 plus B2 is AB1 plus AB2. Another, if this satisfies this, then AB going to BA will also satisfy, and therefore, AB minus BA, this map is also bilinear. So, as one talks of bilinear maps or multilinear maps, one should keep these examples in mind. And now, we can define the concept of tensor product. So, suppose we have two vector spaces U and V. So, then there exists a vector space which is denoted by U tensor V along with a bilinear map from U cross V to U tensor V, such that given any other vector space W and a bilinear map T from U cross V to W, there exists a unique linear map T tilde from U tensor V to W, such that that condition holds, and this entire thing is better expressed through diagrams like this. This means that, of course, we have a bilinear map tensor, we have a bilinear map T, and then given any T, there exists a unique map T tilde such that T is T tilde composed with tensor. So, this equation is expressed through this kind of diagram, and this is an assertion actually that given any two vector spaces, there exists a vector space and a map with this property. Okay. So, let us spend some time with this concept and how does one play with this. So, we want to define a map called flip from U tensor V to V tensor U. So, I define sigma of U V going to V U. This is a map from U cross V to V cross U, and then you observe that this map, you first apply sigma and then you apply this tensor, and then you can verify that this map is bilinear. As this map is bilinear, our condition says that there exists a linear map from U tensor V to V tensor U such that this diagram commutes. That means, sigma tilde composed with tensor is tensor composed with sigma. So, kind of even without knowing this what this is, just by playing with this definition, one can conclude existence of a map like this. Another important concept, tensor product of linear maps. Suppose we have two linear maps T1 and T2 from U1 to V1 and U2 to V2, then you can have this map which takes U1, U2, maps it to T1, U1, T2, U2. This is a linear map, and then this composition is bilinear. You can verify this is bilinear, and therefore, there exists a linear map from here to here denoted T1 tensor T2 such that this diagram commutes. So, remember these constructions carefully. If I have linear maps, then I can define a linear map from U1 tensor U2 to V1 tensor V2 such that such a diagram commutes. So, earlier we defined tensor product, kind of it was an existential thing, but now let us see how does it look like concretely. So, suppose U is a vector space with basis and V is another vector space with basis F1, F2, Fm, then U tensor V is an nm dimensional vector space. This is n dimensional, this is m dimensional. So, this is an nm dimensional vector space with basis denoted by this. In the finite dimensional setting, only invariant is its basis. Therefore, if I as soon as I specify its basis, I have specified the vector space. And so, we have seen that there is a map from, so U cross C to U, I define a map phi, namely phi of U comma lambda is lambda times U. Lambda is a complex number, U is a vector here. So, this map is bilinear, you can verify. Therefore, this map will induce a map phi tilde. Similarly, I can define another map from C cross U to U like this. This will induce another map, and then we know that this is one dimensional, this is n dimensional. So, this is really n dimensional, this is n dimensional, this is also n dimensional. I have a map Next assertion, same here. This is n dimensional, this is n dimensional, and we have natural maps. The assertion says that these maps are actually isomorphisms. So now we want to define the concept of an associative algebra. At this part, kind of we will need quite a few algebraic concepts. So we want to define the concept of unital associative algebra. It could be defined much easily, but we are doing this because then the definition of the dual object becomes easier. So A is a vector space and M is a map from A tensor A to A. It is called the product map, and eta is a map from C to A called the unit. And then these maps are required to satisfy the following kinds of conditions. So I take 3 copies of A tensor A tensor A. Now I have a map. So I have M from A tensor A to A and identity map from A to A. Therefore, M tensor identity is a map from this object to this object. So I have this composition. From here to I can pass to M tensor identity, then M, or from here to here I can pass through identity tensor M. So this component goes here through identity, these two comes here, and then I have this composition. It says M composed with this is same as M composed with that. Here also something similar. From A tensor C I have an isomorphism which we just stated. This is identity map, and here to here I have this map identity tensor eta. Then I multiply, same thing. So these conditions can be written down much easily. Namely, if we make use of this notation that M of A1 tensor A2, if we denote this object by A1 dot A2, then this condition means this one. You first multiply, that is M tensor identity. You first multiply 2 components and then you multiply the third component, that is this path, and this means you first multiply A2 dot A3 and then you multiply by A1. So these two are same, that is associativity. So this diagram represents associativity, and these two diagrams represent this fact that eta of 1 is a unit for this algebra. So this is our usual concept of an associative algebra. So A has an associative product and it is unital, eta 1 acts as a unit. So if we have an associative algebra, then A tensor A also becomes an associative algebra as follows. Namely, I want to define a multiplication map. So take 2 copies of this object, they are tensor products. So A tensor A and then A tensor A. From there, I have to pass to here. I want to define a multiplication map for this object. So that is defined as follows. So these two are kept intact, and I apply the flip operation here. So I apply flip and then I apply M tensor M. And I also define this map eta 2. C is isomorphic with C tensor C, and then from C tensor C I go to A tensor A. So this becomes also another associative algebra. So if A is an associative algebra, then A tensor A is also another associative algebra. Now we want to come to the example of interest for us, namely CG, algebra of functions on a group. So we have a group G. Now of course we are not assuming G to be abelian, G is just a finite group. We consider all possible functions from G to complex numbers. Of course, this is a vector space and this is an algebra also under pointwise multiplication, and CG tensor CG is isomorphic with C of G cross G. So CG is an associative algebra. So you need to define the product law. So it is pointwise multiplication. F1 dot F2 at G is F1G multiplied by F2G, and the unit of this group is the constant function 1. Because if you multiply a function by this function, you get back the same function. And of course, this product law satisfies associativity. So once we have this concept of algebras, we also need its dual concept, namely co-associative co-algebra. So again, we have a vector space, and now in the earlier case, we have a multiplication map from A tensor A to A. While dualizing, these maps change their direction. So this is A to A tensor A, and of course one puts a co. That map was called product, this is called a co-product map. And similarly co-unit. Unit was a map from C to A, co-unit is a map from A to C. The entire thing is kind of reversed. So earlier we had a map from here to here and A tensor A to A. such that that diagram commuted. Of course, now we demand that entire thing is reversed, all the arrows are reversed in this picture also. So, CG is a co-associative co-algebra. So, we need to specify a co-product map and co-unit for this one. So, co-product is given by. So, note that CG tensor CG is isomorphic with C of G cross G. Okay. So, delta of f should be a function of two variables. So, delta G of f on G1 comma G2 is f of G1 G2 and epsilon G of f is f at identity. Then we can verify that it satisfies the conditions, namely these diagrams commute, and it is these things which I leave, and of course, later on you should download these slides and verify these conditions for yourself. Okay? These are very simple linear algebra, but it gives you a feeling of the things and helps you to keep things in mind. So, we have this concept of algebra, we have this concept of co-algebra, and then one puts both these concepts in a box, and that is called bi-algebra. So, bi-algebra is simultaneously a algebra and a co-algebra. So, we have a vector space V, a unit and a co-unit. We also have a product map M and a co-product map delta. So, here we see all the diagrams. So, as M is a product, M is required to satisfy these conditions, and as delta and epsilon is a co-product and co-unit, they are also required to satisfy these. And now, here you see that here these arrows are kind of in reverse direction, same here. But these maps must be compatible among themselves. So, they cannot be independent. So, delta must satisfy certain relations with respect to M, and that is the following. So, epsilon, this map must be an algebra homomorphism. That means, epsilon of A1 dot A2 must be epsilon A1 dot epsilon A2, and this map delta from A to A tensor A. Now, we just saw that A tensor A is also an algebra. So, it has got its multiplication, and delta must be a homomorphism. So, delta of M must be M2 composed with delta tensor delta, and eta 1. So, epsilon maps this identity of the algebra to 1, and delta is also unital. So, delta of identity of this must go identity tensor identity here. So, such a thing is called a bi-algebra, and of course, in a group we have seen that a group is an algebra, CG is an algebra, CGA is a co-algebra. Only thing one has to verify is that those relations satisfy these conditions. Separately these are verified, they will also satisfy these conditions. So, CG is actually a bi-algebra. Another bi-algebra of interest is the group algebra. So, we are denoting it by C star G. So, it is the span of elements. So, given any element G here, you consider its span of xi z, and there you define a multiplication law as follows. So, this gives a basis. So, m g star that takes xi g tensor xi h to xi of g h, and delta of g star takes this one to xi g tensor xi g. Eta g star is a map which takes, it is the unit. So, 1 goes to this element, and similarly epsilon g star is this one. So, we have this concept of bi-algebra. Now, that is further extended to this concept of Hopf algebra. So, Hopf algebra means it is a tuple like this, where these parts correspond to a bi-algebra, and there is another extra map S. So, this map S is called antipode, and so if you look at carefully at both these examples, CG, so CG G is a set, and that set structure is encoded in this group law. So, on this algebra of functions. For example, the only invariant of G is its cardinality, and that is encoded in this thing as the dimension of this vector space. So, as a set, G is described by this structure, namely if you count the dimension of the vector space, you understand G as a set. Next, you want to understand G as a group. So, you want to understand the multiplication law of that group, and that structure is encoded in this map actually. So, as we pass from group to this structure, various structures of the group are encoded through various operations of these linear spaces. And so, we have encoded the group the set structure and the multiplication structure. The thing that is remaining is the inverse. Here also something similar. No, this is not underlying a group, no. So, we will come back to this thing later. So, we need to encode the operation of inverse in these algebraic structures, and that is encoded through this operation. So, S is a map from A to A such that, so if you first apply delta, so delta maps you A tensor A to A, then you apply S tensor identity. So, that again from A to A tensor A, and by M you get single copy. So, this is from A to A. Similarly, this one you first apply delta, then identity tensor S, and then M. These two compositions are same as this one. Again, so you have delta, you have S tensor identity and M, that is this. Then again delta, identity tensor S, and M, that is this. So, in the concrete example, if the functions on the group, what is S? Sg of f on G is f of G inverse. So, you see that this operation for this special case encodes the operation of G going to G inverse. So, this information is encoded in this linear map. Similarly, in this case, Sg star from C star G to C star G. So, Sg star of xi G is xi G inverse. So, now we come to this concept of duality for Hopf algebras. So, in the group case, we had a group and its dual. So, if instead of group we are, so the idea is that Hopf algebras kind of encode groups. So, this passage from G to G hat, we should have a lifting of this concept in this setting. So, that is done as follows. So, we have a Hopf algebra H with its multiplication and coproduct, unit, co-unit and antipode. Then we consider this space H star, and H star is the space of linear maps from H to C. Then we have map from H star tensor H star to H star. So, note that H tensor H star is naturally isomorphic with H tensor H star tensor H star. So, this is isomorphic with H tensor H star. Okay. So, this is isomorphic with H tensor H star, and now you go back. As H is a Hopf algebra, H has got its coproduct map. So, we have a map delta from H to H tensor H. Therefore, delta star will be a map from H tensor H star to H star. That is this map M star. Okay. So, M star is actually a delta star, and if we write down explicitly what it is, so M star of phi 1 tensor phi 2 acting, so it is an element in H star. So, acting on A is phi 1 tensor phi 2 of delta A. Similarly, this one, we have a map M from H tensor H to H. So, M star is actually a map from H star to H tensor H star, which is isomorphic with this object. So, delta star is actually that. Okay. So, there is a possibility of confusion, that is why I could not write it down that delta star is M star, because then it gets confused with this one. So, delta star of phi on A1 tensor A2 is like phi of M A1 tensor A2. So, phi is here. So, it should act on H tensor H star. So, you take an element A1 tensor A2 from H tensor H, and this is prescribed by M of A1 tensor A2 is an element in H, phi of that. Similarly, this is the dual of the co-unit. So, eta star 1 of A is epsilon A, and it is the dual of the unit. So, star phi is phi of eta 1, and A star is the antipode. So, it is dual of H to H, this one. Okay. And so, we are more or less done with the terminology. So, it looks like that it will be over quickly. So, the theorem says that if you have a Hopf algebra H, then this object is also a Hopf algebra. Okay. So, proof is also very easy, because you note the following thing, that in the definition of Hopf algebra, that is first a bi-algebra, and then it satisfies one more condition. Now, these conditions are kind of self-dual. So, H satisfies these things for its multiplication and co-multiplication, and as you dualize, we saw in the first slide that the arrows, direction of the arrows are reversed. Therefore, if H satisfies these conditions, then H star with its dual maps will also satisfy these conditions, and this one is also easy to verify. Therefore, it is just a linear algebra, which kind of one should go back and check that H star is a Hopf algebra and called the dual of H. The next one says that, of course, we had an isomorphism between V star star and V. So, one could further follow that. So, if we take dual of this object, then we get something which is naturally isomorphic with this. So, this fact that this is isomorphic is actually an exercise in again the fact that V to V star star, that map is natural. Okay? Naturality of that isomorphism will actually imply that this entire structure is isomorphic with this. Naturality of that will imply that star of this, so M star star and M eta star star and eta, these objects will be respected through this isomorphism. So, these two parts are easy. Now, this one says, this one relates. So, starting with a group G, we had two things, namely C star G, and this is one Hopf algebra, this is another. Now, of course, this one is not true in general. So, this is true if no, this is true in general. Sorry, this one does not require anything. Sorry. So, it is just again a direct verification. Okay. So, I will comment about this proof soon. Next one requires G to be abelian. Okay. If G is abelian, so for a general G, we constructed two Hopf algebras, and this proposition shows that these two are related really. This is the dual of that, and next one tries to kind of identify this object in terms of G hat. So, it says if G is abelian, then C star G, M star G, this object which is cooked up using G, and this is cooked up using G hat. So, these two objects are isomorphic if G is abelian. Okay. So, proof I indicated that the definition is self dual, from which this one follows. This one is an exercise in the naturality of B going to V star star. This one, so note that C G has basis delta G, namely delta G are the functions, delta G of H is delta G H. So, it is equal to 1 if H equal to G, otherwise it is 0. So, these functions form a basis of C G, and now if you want to write down the multiplication and co-multiplication in this basis, then you will realize that M G of this object is really, if both of them are same, then it is delta G, otherwise it is 0, and delta G of delta G is given like this. So, xi G is the dual basis of this object. Okay. So, basis for this and basis for this. So, we already defined this object through a basis xi g, and this we have this basis delta g, and these two bases are dual to each other. And not only that, these maps are also dual to each other. Okay? So, m g star, if you just verify, kind of compute this quantity, you realize that this is same as this is also same as this. So, that shows that m g star is dual to delta g. Similarly, these two and the other conditions also, namely eta and epsilon, they are also dual of these objects. So, point is the following, that C star g can be described as dual of this, and C g hat is this. Now, of course, this is the final slide. So, the spirit is the following: G encodes a group, encodes a certain amount of data or structure, namely it is a set along with multiplication law, and the same structure is encoded in this Hopf algebra C g. Okay. So, we have a rough feeling about it. For finite groups, maybe you can try to verify how to do that, but we can see that for example, the set structure is encoded in its dimension, then its multiplication structure is encoded in its coproduct, and then of course, inverse is encoded in the antipode. So, the entire structure of G is encoded in this Hopf algebra C g. Then there are two ways. From G, we could pass to this group G hat, or from C g, this is a Hopf algebra, by duality we can pass to this object. Now, note one thing, that even if G is non-abelian, we can always pass from this Hopf algebra to another Hopf algebra C g star, which is isomorphic with C star G. This part does not require G to be abelian. If moreover G is abelian, then we realize that this thing is same as C g hat. So, in case we were encoding our groups through this structure, then this duality of Hopf algebras respects this structure of passing to Pontryagin dual. So, if G is encoded in C g, and this duality of Hopf algebras, if we restrict them to the duality of groups, then kind of this diagram is consistent, and of course, then we can do it twice. So, if G is abelian, then we can pass to G hat hat. Here we can pass to dual of this. Of course, C g star star is isomorphic with C g, and this is same as C g hat star, and that is C g hat hat. So, if we record, instead of recording the group structure, if we record its Hopf algebra structure, then we see that this concept of passing to dual actually encodes this information of Pontryagin dual, and this map that so this is like H is isomorphic with its dual of its dual. Okay? This isomorphism is actually Pontryagin duality, right. So, this is like C g is isomorphic with its double dual. This map, this part makes sense even if G is non-abelian, whereas this one requires if G is abelian. So, these two isomorphisms are consistent. That means that this line of argument extends the usual understanding of Pontryagin duality. That is all, and you can download this and kind of go through the linear algebra by yourself. All this involves is very simple linear algebra. So, you can download this and go through the linear algebra. That is all.